We're glad that you could join us today. It's nice to see that we have attendees from like more than 30 countries from what I can see. My name is Michel Paradis. I'm your host for this webinar on multi-caliber quantitative analysis. I'm a senior product manager here at Ultra Electronics Forensic Technology. Our presenter is Dr. Danny Roberge, a senior scientist in our research and prototyping group. Having joined our company more than 20 years ago, he holds a doctorate in physics for optical pattern recognition. He was awarded a fellowship for a postdoctoral project related to optical fingerprint identification and biometric encryption. He has developed algorithms for IBIS related to the acquisition and correlation of bullet and cartridge case images. He is also the author and co-author of several patents in the field of automated ballistic identification. Today, Danny will explain our latest breakthrough with a new generalized method that now provides similarity measures and false match rate for multiple firearm calibers. Danny had introduced an early version of the RBL method, or I pronounce it Rebel method, a few months ago during our online launch of the Quantum 3D microscope. For those who did not attend that May 28th online launch, please note that there is a recording of that event on our website, and it provides a more complete description of the product as context for today's more scientific topic. The length of the presentation will be about 50 minutes today. If you have questions, you can use the chat feature of the GoToWebinar interface. We might have some time at the end to address them. We will also provide some email addresses on the last slide, giving you more time to formulate questions and also for us to answer them appropriately. Now, I'll turn it over to Danny.
Good morning, everybody. So here's the outline of my webinar today. We'll start, of course, with a little recap of what I presented a few months ago concerning quantum 3D microscopy. We will follow with the analysis of other calibers. Looking at different, what we call FAM combination. F is for firearm calibers and brand, A is for ammunition type, and M is for bullet material. We will, I would say, study class characteristics and roughness variables, and those variables are derived directly from the 3D measurement, from the digitized bullet lead profiles. We will quickly explain our synthetic lead profile generation method that will help us to derive the score adjustment process, which is the core of that presentation, for combining different data sets on the same RBL graph. We will introduce the generalized RBL graph, and we'll finish with the conclusions. So I think we can say that topography will be no longer visualized using transient lighting conditions. It will rather be measured and permanently stored on a computer. Virtual microscopy provides greater availability for reproducible comparisons. At that time, at the first webinar, the model was trained with only 9mm bullets only. Quantitative models provides first graphical depictions of similarity scores and provides a statistical model to support the expert conclusions if he actually wants to go in court. So if you want to have detail about that statistical model, we actually published a paper last year and it is open access, so feel free to download your own copy. So just like biometrics, fingerprint identification, iris pattern recognition, and DNA sequencing, ballistic identification must be supported by a probability of making a wrong call. So that's why we developed the Quantum 3D Microscope S1, that is a new comparison system with a quantitative component. This is our certified quantum acquisition unit, where we provide pilot cameras for orientation, auto-centering, auto-focusing. We have an intelligent surface tracking system that actually can acquire those kind of funky shape. And the 3D data is always split in two levels of resolution. The first level is the waviness, which is the overall shape, and the roughness is the detail of the surface of the bullet at the micron level. To visualize those two levels of resolution, we have two viewing modes. The first one is a surface view, where we actually see the mosaic of roughness that is basically an honorable carpet of the surface of the bullet. And the other mode is the shape view, where we can see the entire set of 3D data. And finally, the error estimation through the RBL graph that we will explain in detail in the next few slides. But first, let's start with the definition of making a wrong call. Well, that's the probability that a system incorrectly identifies a pattern X with a pattern Y. It is basically the false match rate that they're using in biometrics. Today, we intend to evaluate that, but for ballistic. Whether we have a pristine bullet like this one or damage or fragment, we always provide two sets of information. The first one is the 2D information that we call the reflectance. The second one is the 3D information that we call topography, that we split, as we said, in two levels of resolution, waviness, but more importantly, the roughness that contains the relevant correlation information. So here we have the mosaic of the roughness of a surface of a bullet. The first thing we do digitally, we extract all the individual land engraved area. And for each of those land engraved area, we extract the most relevant Lie profile. And within Quantum, we compare those profiles to get the objective identification score D. So here's a little flashback or coming back to the first webinar. At that time, we had access to 136 firearm, conventional rifling, 9mm only. We had a total of 422 known matching pairs that we visually inspect, and we end up with 235 visual matching pairs. On the graphic, we see the related correlation score. We have 235 visual matching scores right here, and we have 80,000 known matching score. On the horizontal axis, we have the pattern matching score. That is a linear combination of two standard methods, the well-known cross-correlation function and the absolute normalized difference. And the pattern matching score is looking at the global similarity of those profiles. On the vertical axis, we have the line counting score. That is looking at those fine lines that we call stria. The line counting score is looking at the matching stria pattern. It depends on two variables, the density of those matching stria, and it depends on the number of an independent group of consecutive matching stria. We are actually combining two schools of thinking or two philosophies, line counting and pattern matching, on the same RBL graph. The RBL graph provides a separation line as well. It actually split between non-match and visual match. What is the false match rate associated with this separation line? Well, it is the chance that two non-sister bullets generate a correlation score above that separation line right here. If we have 80,000 non-matching score right here, and if we look closely, there's only 8 of them that reach the line and actually go above that line. So we have a ratio of 8 over 80,000, which is 1 over 10,000, which is 1 over 10 to the 4th. This is the proportion of non-matching score above the separation. It is my false match rate for my separation line. Now, if I apply a minus log on my false match rate of that line, I get the number 4 that I define as the false match rate index of my separation line right here. The graphic provides a false match rate index set of isoline. That line corresponds to a false match rate of 1 over 10 to the 4. That one corresponds to a separation line of 1 over 10 to the 6, and so on like this. To fully understand how the RBL graph works, we actually took a suspected matching pair of bullets and correlated them together to get that correlation score right here. The location of that correlation score on the graphic allows me to draw two conclusions already. The first one is that this pair of bullets is likely to match visually on a comparison microscope, because that's the way we train the system. I mean, if we have two bullets and it generates a score above that red line right here, well, those two bullets that generated that score will present visual similarities. And secondly, that score is on the isoline of 6, which means that there's only one chance over 10 to the 6, which is 1 over a million, that two non-sister bullets generate a score like that one or greater than that. It is the false match rate value that you guys want to bring in court. So what is officially my objective identification score? We have our two distribution right here, visual matching score, non-matching score, and intuitively, it should be somewhere right in the middle. But more systematically, what we're doing, we're looking at the direction of the visual matching score, and we actually project all those individual points on that axis. And the objective identification is the length of that yellow vector that represents the projection. D is because it's the distance from the origin to that projection right here. And you'll realize that as this vector increase, well, the visual matching agreement is getting better. And finally, this objective identification score is a linear combination of the pattern matching score and line counting score. So we collapse the problem to a 1D problems and end up with those two distributions right here. The gray one on the left, is the non-matching objective identification score D distribution. The white one on the right is the visual matching objective identification score D distribution. Now, from now on, I can actually set a decision line and make that decision that any pair of bullets that creates a correlation score above that line will be considered as being shot by the same firearm. But taking that decision has a consequence. We have a portion of the non-matching score distribution above that line, and this is my false match rate. It is the probability that two bullets will be by mistake identified as being shot by the same firearm. Here I have the false match rate in function of the objective identification score. If I set a decision line at 0, well, we have 100% of the non-matching score distribution above. We have a false match rate of 100%. If I raise that up to 0.5, well, I have 10% of the non-matching score above that line. So we have a false match rate of 10%. But if I keep raising that up to 0.7, there is no non-matching score above that. So do I have exactly 0% for false match rate? It's kind of sad because this is where I would like to have really high precision. So this is why we actually switch to the logarithmic scale over here for two reasons: to have a focus and to have detail of the tail distribution, and secondly, to be able to extrapolate. So if I'm looking for a score of 0.7, now I can actually evaluate the false match rate index equal to 5, which is a false match rate of 1 over 10 to the 5, which is a false match rate of 1 over 100,000. This curve will be referred as the false match rate curve, and keep that in mind. Okay, we will use this curve constantly from now on. Okay, now we jump really in the core of that presentation. I mean, analyzing other calibers, firearm calibers and brand, ammunition type, and bullet material. And in that section of the webinar, we will explain first what we found analyzing other calibers, and secondly, how we generalize the method to other calibers. So, firearm calibers example, 9mm 25 auto 357. Firearm brand example, Beretta, Colt, Mossberg, Browning, Remington, Winchester, name it. Ammunition type, Federal, R&D, Marlin, and finally, bullet material, copper, brass, lead, nickel. Now let's say we have a matching pair of bullet A1 and A2. They were shot from the same firearm, but they may or may not be from the same ammunition. They may or may not be from the same material, but still, they will produce a pattern matching and a line counting score. Now let's say we have a data set of matching pairs like this one, A1, A2, B1, B2, C1, C2. If we correlate them together, that will generate two distributions. The matching score distribution and the non-matching score distribution. That will be driven by the FAM combination of that data set. What do I mean by that, driven? Well, if I'm looking on the RBL graph, my non-matching score distribution will be moving depending on the FAM combination. And if it moves, well, the separation line will be moving, and the false match rate index of isoline will be moving as well. So we can say that if we have n calibers data set, we'll have n different FAM combination, and we will have n different RBL graph to manage. We may not want this. We want the correlation score to overcome that FAM dependency to actually give a unique generalized RBL graph that will provide a static separation line, a static false match rate set of isoline. As you will see, the correlation score here must have a totally different purpose than IBIS. In fact, there are 3 correlation score purposes or categories as defined by the OSAC committees. Category 0 is for ballistic search, just like IBIS. We have a list of correlation score that we rank from the highest down to the lowest, and the score itself doesn't mean that much. It's really the rank. We are not interested in category 0 in that webinar. Category number 1, score value first quantifies absolute similarity, carry the same degree of confidence, allows the definition of a unique threshold value that discriminate pairs of bullets that require more in-depth analysis by the expert. This is exactly our separation line. And finally, is not or weakly sensitive to an FAM combination. Category number 2, the probability value is measured from a statistical distribution of correlation score, for example, false match rate. And here again, it's not or weakly sensitive to an FAM combination. Otherwise, a threshold value must be defined for each of those FAM combinations. And here again, we may not want this. So here's an overview exactly of the challenge we're facing, okay? Let's say we have 2 different FAM combination RBL graphs. On the left, we have the first combination, FAM1. On the second one, we have second combination, FAM2. And we just said that the difference is the location of the non-matching score, which means that we have different location of separation line, and we have different location of the false match rate index supervised line. Now, let's say we have a suspected matching pair of bullet with the second combination right here. We put that on Quantum, get the 3D information, and we get the correlation score that falls right over here on the second graphic. Now, let's say we actually decide that this is my reference RBL graph. Now, a good question is that what would be my equivalent score on that graphic right here? Well, the equivalent score should preserve the same visual similarity and has to preserve the false match rate value. So that score should be right here, same false match rate value. But the pattern matching and line counting score is right over here. So we have to do some score adjustment to get the equivalent correlation score. The score adjustment process should be derived from the 3D data and must preserve the false match rate value as we said. So that way, we will always refer to the same RBL graph, and the process will be FAM independent since the score adjustment was derived from the 3D data, and this doesn't take any information whatsoever of the FAM from those 2 bullets. So this is exactly what we will try to do today, try to find that score adjustment to give me an equivalent score on the unique generalized RBL graph. But is that true what I just said, that different FAM combination change non-matching score distribution location? Well, to answer that question, we need to acquire several datasets. My first dataset that I call my reference dataset is 9mm caliber. We have 65 sister pairs for a total of 130 bullets. I actually picked 65 visual matching pairs among the 235 I had at the first webinar. And the reason why is because I chose the one that has rigorously the same leeway. Now for consistency, we acquired the same amount of sister pairs for all the other 4 calibers. In all those 5 datasets, I have 2 different materials, and I have 2 different groups of numbers of leads, 6 and 5. No need to say that in those 5 datasets, we have different calibers and brand, different ammunition type, and different material. Now, if we go back to our question, what is the behavior of different non-matching score distribution on the RBL graph? Now, let's start with our reference dataset, 9mm. You probably noticed that we have 2 reference lines right here. We have a reference circle that will give me the location of the non-matching score for my reference dataset. And I have this line right here that tells me the location of the separation line for my reference 9mm dataset. You probably observed that the separation line is slightly different from the one we presented at the first webinar. And the reason is quite simple. At that time, my only criteria is only using 9mm bullet, which means that the datasets probably have leads and copper bullets, and we have various leeward values. In that case, the dataset is way more homogeneous, and I only have copper bullets. And as I told you, we chose the leeward that were rigorously the same, which is about 650 pixels. Here's a little details. We have a resolution of 3 microns per pixel, which correspond to a leeward of 2 millimeters or 0.08 inches. The white dots over here indicates visual matching scores. And as I told you, we picked 65 visual matching scores, so they all have white dots. And furthermore, they are all above the separation. Now I think it's time to look at the other datasets. If we start with 25 right here, first thing we notice, there's some point with no white dots on top, which means that we have several non-visual match. But more importantly, we have a shift of the non-matching score distribution to the right, which bring a shift of the separation line respect to 9mm. But we realize that most of the white dots are above the new red separation line. For 22, it's about the same thing. We have a shift of the non-matching score to the right. So we have a shift of the separation line to the right respect to 9mm here again. But here again, most of those visual matching score are above the red separation line. For 45, it's slightly different. We have a shift of the non-matching score towards the pattern matching score axis. Then we have about the same separation line in 9mm. And here again, most of those visual matching score are above the red separation line. And finally, for 357, here again, it's slightly different. We have a shift of the non-matching score towards the origin. So we have a shift of the separation line in the same direction. And here again, most of those visual matching score are above the red separation line. So what can we conclude from those observations? First, we all have different separation line location, but still, the separation line always split non-visual and visual match. My 5 data sets, they all have different FAM combination, and it generates different separation line locations. So to get the same separation line location, maybe we should remove this FAM dependency. So to understand that FAM dependency, let's have a look at a really specific correlation score, but for 2 totally different data sets. So we chose 9mm where we only have copper bullets, and we chose 22 where we only have lead bullets. In that case, we have a shift of the non-matching score to the right, and we have a shift of the separation line to the right as well. Now, if we click on that correlation score, that score is above the separation line for 9mm, which means that the 2 bullets that generated that score probably present strong visual similarities. That's the way we train the system. And as a matter of fact, we took the 2 pair of leads with the highest score, and as you can see, we can see strong similarities. If we click on the same correlation score for 22, now the score is below the 22 separation line, which means that the 2 bullets that generated that score may not present visual similarities, because that's the way we train the system. And as a matter of fact, we took the 2 pair of leads with the highest score, and we cannot actually match them. So we can actually conclude that for 2 different FAM combination data sets, for example, our 9mm and 22 right here, the same pattern matching score and line counting score do not quantify the same visual similarity. That's what we just proved. Okay? And secondly, do not quantify the same false match rate value. In that case, I have a false match rate index of 3, and in that case, I have a false match rate index of 5. So my question is, keeping the same false match rate value, where would be my 22 correlation score on the 9mm RBL graph? So it means I will have to do some score adjustment. So here comes the score adjustment process. Here again, we should be derived from the 3D data, and it must preserve the false match rate value as we just explained. But to preserve that false match rate value, there's 2 criteria. The first one, we need the false match rate curve of my reference 9mm dataset. That one is quite easy because we can actually pre-compute that. We have all the data. But the false match rate curve of my suspected matching pair of bullet right here, where everything starts, it's another ballgame. But you will see that we find a way to compute false match rate curve for any suspected matching pair of bullet. We will explain that in detail. This is the core of the score adjustment process. We'll explain that in section 4. Okay, observation. Marks created on bullet are sensitive to FAM combination, firearm calibers and brand, ammunition type, and material. The number of FAM combination is absolutely huge, which means managing a huge amount of different RBL graph. We may not want this. So here's my hypothesis that is really important right here. Despite the large number of FAM combination, caliber behavior could be generated by a small number of class characteristic and roughness variables directly measured from the 3D data from the individual lead digitized profiles. We assume dependency only through class characteristics and roughness variables, which means CNR variables exclude the FAM variables out of the problem. Physically, it's not exactly that. It's that the CNR variables embed the FAM information. So for example, I have a bullet here that was shot by a Remington gun that used an R&D ammunition and is in copper. That bullet has 6 leads, so we acquire them on Quantum, so we have the 3D data where we extract the digitized D profiles. And from that, we get class characteristics and roughness values. And my hypothesis is that these values embed the FAM information. So this is what we will try to prove. So understanding CNR variable extracted from profile is absolutely crucial. So this is why we will study class characteristics and roughness variables derived data derived from the bullet profiles. We are considering three variables. For class characteristics, we are considering the individual lead width and the number of leads. For microscopic roughness variable, we'll be considering peak and valley heights, width, or slope. So to understand and isolate the effect of CNR variables on the collation score, we created the following very simple academic model that really speaks by itself. We will not be using our pattern matching and line counting score. We will rather use the well-known standard cross correlation function score that is defined that way. X and Y are the individually simulated profile, delta is the optimum relative shift, and CCF max is the related cross correlation function score for the optimum shift. In fact, we just shift the Y profile respect to X by dx pixel, and when we reach delta, we optimize similarity to get an optimum correlation score. Computed profile in my model right here depends on two parameters. The first one is the lead width. The second one is a roughness parameter, alpha. Physically, alpha is more a roughness visual aspect tuning parameter that we can change from 0 up to 1. If we choose 0, it means all those pixels are totally independent. So we are generating basically white noise profile. But if we raise alpha up to 1, 0.25, 0.5, 0.75, we start to see structures appearing, which means that we have dependency through neighbor's pixel. But when we get the value of 1, we attain the full dependency, which means that the profile has a unique value. It's actually constant, as you can see. So alpha is just changing the visual aspect of roughness. Now, let's do some simulation. So we start with alpha equal to 0. So we are basically generating white noise profiles. So we randomly generate 1,000 pairs of white noise profiles. We correlate them together so we have access to 1,000 cross-correlation function score to do statistics. We are basically simulating non-matching score distribution. We do that experiments for several lead width value, from 100 up to 1,000. And if we choose an arbitrary score of 0.4 here, the chance of having a score of 0.4 here it's not big, but it's not 0. But if we look for 1,000, the chance of having a score of 0.4 is absolutely 0. So the chance of having a high score by totally pure chance is higher for a small lead width. Now, if we change alpha up to 0.75 and do exactly the same experiments, generating 1,000 pairs of profile, changing the lead width, we actually see that distribution have changed. So different roughness characteristic, just changing alpha influences the CCF score statistics as well. So in the latest example, varying the class characteristics and roughness values change the CCF score. In fact, even the well-established standard CCF score is affected by a lead width and roughness variation. It changed the pattern matching and line counting score in our RDL graph. They're very similar. And here's an example. We have two data sets right here. The blue circle indicates the 9mm non-matching score location right here. The red circle indicates 25 auto non-matching score locations right here. The difference between those two data sets is basically the lead width because we have copper bullets, we have the same number of leads, and the roughness variable values are about the same. So we just have a lead width from 650 down to 400. In the consequence, we have an increase of the cross-correlation function score for 25. And since it is embedded in the pattern matching score, well, we have an increase of the pattern matching score for 25. This is exactly what we're seeing here, and it's totally consistent with our simple model. So to understand that dependency of the pattern matching score and line counting score over CNR, we need to explore several CNR values, and there's only two ways to do it. Acquiring way more data sets or generating way more data sets synthetically, and this is why we created our own synthetic model. And I want to be clear here. I want to make that clear is that synthetic model by itself is a topic. I could actually do an entire webinar on that model, but it's not the point here. I'm going to use this as a tool. So our synthetic model creates personalized lead profile with respect to the statistics of each category. So that way, we can study the effect of changing the lead width, number of leads, and as you will see, the absolute local slope with simulation in a controlled environment. But first, let's have a look at real profiles, CNR, variable statistics. Of course, we use our reference data sets where we have access to 130 bullets with 6 leads. That gives me nearly 800 real lead profiles. For each of those profiles, we split them in 2 levels of resolution, Y smooth and Y detail. And if we focus on Y smooth, we can extract a series of relevant points, and we can do statistics with the relative position of those points. But still, for class characteristics variables, we are considering lead width and number of leads. Here we have statistical distribution of lead width for those 800 profiles. For roughness variable, we are considering the slope of those consecutive peak and valleys right here and retain the absolute local slope. So at the end, we are retaining 3 variables, lead width, number of leads, and the absolute local slope. And you'll see those 3 variables will provide each individual dataset signature. Let's look at this. So we have our reference dataset. This is the statistical distribution of the lead width with an average value of 650 pixels. This is the statistical distribution of the absolute local slope with an average value of 0.07. For 25, we have about a lead width of 400 pixels. We have about exactly the same slope. We have the same material, same number of leads, same slope. The major difference between these 2 datasets is the lead width, as we have seen. Consequence, we have much higher pattern matching score. For 22, we have a lead width of 350 pixels. We have a slope a little bit lower. For 45, we have a lead width of 650. We have about the same material, copper. We have the same number of leads. The difference is we have a much lower slope right here. And what is the consequence of having a lower slope? Well, if we look at the slope of 0.07, we have peak and valleys, and the peaks are really high, so it's easy to reach the criteria of being a striatum. Okay, but when we actually decrease the slope value, we still have peak and valleys, but most of them do not reach the criteria of being a stria anymore. So the consequence of that is we have much lower density of matching stria, which actually decrease my line counting score, and this is exactly what we observe right over here. For 357, we have much higher lead width value. We have a slope that is about the same as 22, and we have 5 leads instead of 6. The consequence, we have lower pattern matching score, and we have lower line counting score. But still, each of these data sets has its own CNR set of values. Now, synthetic lead profile generation. From the class characteristics and roughness variable statistics, we will compute first synthetic profiles, and from those synthetic profiles, we will compute the synthetic non-matching score distribution, and from those synthetic non-matching score distribution, we will compute the synthetic false match rate curves, and we'll get the synthetic false match rate curve for any suspected matching pair of bullets. This is what we were missing to do the score adjustment process. Now, like I told you really quickly, we reverse the process. We take the statistics of the CNR variables and find the location of those relevant points to get Y smooth, and we had realistic texture on top of this to get the synthetic profiles. So here as an example, we have real profiles for 25 on the left, and we have this created synthetic profiles on the right. And as you can see, real and synthetic profiles have the very same visual appearance, but that's not the point. The real question is, what about the correlation reproducibility with those synthetic profiles? Okay, now we bring back those real non-matching score distribution, where for 9mm, it's right in the middle of the circle because it is my reference data set. For 25 and 22, the non-matching scores are shift to the right. For 45, we have a shift towards the pattern matching score axis. And for 357, we have a shift towards the origin. Now, how can we produce synthetic non-matching score distribution? Well, we take the same amount of sister pairs, we take the CNR variables for that caliber, reference caliber right here, and we create those 65 sister pairs, synthetic profiles, collate them together, and only retain the non-matching score distribution. And as you can see, they are nearly identical. Now, we do the same thing for 25 and 22. Create the synthetic profiles for 25 and 22, and we reproduce the shift to the right. For 45, we reproduce the shift towards the pattern matching score axis. And for 357, we reproduce the shift towards the origin. So we actually preserve statistical dataset personality. Well, let's go a step further. What about the false match rate curves? Here again, we have all the real datasets. These are the false match rate curves for the real datasets. The dotted line is the curve for 9mm as a reference. And as you can see, they all have their own personality respect to the 9mm false match rate curves. Now, if we take the synthetic non-matching score distribution and compute the false match rate curve for synthetic, as you can see, each dataset personality was reproduced. So here again, real and synthetic false match rate curves are nearly identical. I think it's time now to do a little recap of what we've done with our synthetic model. By using every dataset of class characteristics and roughness values, the synthetic model can reproduce almost perfectly first the non-matching score distribution and the false match rate curves. So thanks to our 5 datasets, because of that, we could evaluate the CNR range of values to cover most of the FEM combinations. And secondly, we could generate multiple false match rate curves using predetermined CNR values within that range. It is really important, that point right here. So for example, we have a series of predetermined values of CNR. With that, we can actually pre-compute in advance a series of false match rate curves and keep that on my computer. And with that, as you will see, we'll be able to do the score adjustment. You're probably questioning yourself, how do we do that? Well, here's a little reminder of those totally different datasets. And I had that question, keeping the same false match rate value, where would be that 22 correlation score on a 9mm RBL graph? I told you we need 2 things. The false match rate curve of my reference dataset, but this is easy because we can actually compute that and keep that on my computer. But we have to provide the false match rate curve from the suspected matching pair of bullets, where we started with a correlation score. And we just proved that we can create synthetic false match rate curve for any suspected matching pair of bullets as long as we have their related CNR set of values. And here's how we do this. I have a suspected matching pair of bullets. We correlate them together, and let's say we pick the pair of leads with the highest score. I have those 2 profiles. We correlate them to get the objective identification score, and we can actually get the personalized CNR values. I mean, the average lead width, the average absolute local slope, and we know that they have 6 leads. Now, we keep that in mind. Now we go for the prior information we have already in our computer. I have this false match rate curve already of my reference dataset, and I have those series of false match rate curve that were pre-computed because I have predetermined CNR values. Now, the only thing I have to do to connect these 2 together is looking at those personalized CNR values and point the right false match rate curve that correspond to that suspected matching pair of bullets. Now, that false match rate curve is for those 2 bullets, and that curve is for my reference dataset. Now I take the objective identification score, project that on my false match rate curve for my 2 bullets, preserve the false match rate value, and bring the score back on the axis. That will give me the equivalent score on the 9mm RBL graph. There is no reference whatsoever to the bullet caliber or material in that process of score adjustment. So what we're going to do next is just proceed, do exactly the same thing on the 4 other datasets to see what's the effect on the non-matching score. 25 auto, only copper bullets, about the same slope, same number of leads than 9mm. The difference is within the lead width. The consequence, we have much higher pattern matching score. 22, we have different material, same slope, same number of leads than 9mm, difference 350 for lead width, 650, consequence, much higher pattern matching score. Now, if we actually apply the score adjustment that we just explained, it brings back my non-matching score distribution in the middle of the blue circle. The CNR values actually drive the show. There's no reference whatsoever to the bullet caliber or material in the score adjustment process. For 45, it's slightly different. We have about the same lead width and same number of leads than 9mm. The major difference is the slope, and as we have seen, the consequence is much lower line counting score. If we apply the score adjustment process, it brings back the non-matching score in the middle of the blue circle. And finally, for 357, we have different material, we have different lead width, and we have 5 leads instead of 6. The consequence, we have lower pattern matching score lower line contains score. And when we apply our score adjustment, it brings back the distribution right in the middle of the blue circle. So all those adjusted non-matching score distribution are nearly identical. And this is exactly what we wanted. For a suspected matching pair of bullets, as we said, we acquire them on Quantum, we get the 3D information. From that, we extract the digitized Lee profile. And from these profiles, we get the objective identification score, we get the CNR values, and we actually pass that information to the score adjustment process. That will give me the equivalent score on the 9mm RBL graph. And we have to note that this is for any suspected matching pair of any FAM combination. So now we are ready to combine adjusted correlation score for all our 5 data sets to get our generalized RBL graph. So after our score adjustment, if we look at the top, these are all the adjusted non-matching score, and they are back in the middle of the blue circle, which is my 9mm reference circle. It means that all non-matching score distribution are nearly identical to 9mm non-matching score distribution. This is what we wanted. At the bottom, all adjusted false match rate curves overlap with the reference dotted line that correspond to 9mm. So it means that all false match rate curves are nearly identical to 9mm false match rate curves. This is exactly what we wanted. The only difference is for 45 right here, but it occurs at really low false match rate, and it's 1/10 to the 10. And that difference is within the interval of confidence. So we can actually combine all the correlation score sets. I mean, we will have at the end 5 times 8,320 non-matching score, 5 times 65 matching scores. So after the score adjustment, we will have 42,000 non-matching score, 325 matching score. That we can actually put on a unique generalized RBL graph that provides a unique and static separation line for a false match rate of 1/10 to the 4. That is actually right over here. And what we notice is most of the visual matching score are above that unique and static separation line. The resulting false match rate curve right here, the dotted line is of course our 9mm false match rate curve, but the plain line right here corresponds to our data sets, all data sets combined. And as you can see, we have a perfect overlap. And physically, it means that we remove the FAM dependency. So thanks to our score adjustment computed from the CNR variables. So this is what we actually have on the product. This is my new RBL graph. Okay, so here again, we have a suspected matching pair of bullets that correspond to an FAM combination, but we just don't care. As long as we get the 3D data, we extract the Lee profiles, and from that, we extract the CNR values, personalized CNR values. I mean, the average Lee width, the average absolute local slope and number of Lees, and the objective identification score that we pass on to the score adjustment process. That process removes the FAM dependency and gives me the score on the unique generalized RBL graph right here. You probably notice that those isolines are way more compressed than what we had at the first webinar. And we already explained the reason why. That data set has various Lee width values, and that one has a unique Lee width values. Here the distribution is more spread out, and that one is like a delta function. The consequence, we have a false match rate curve that drops more rapidly. And if we project a series of false match rate index, let's say 4, 6, and 8, well, the D values are way, way, way close to each other compared to what we had before. It explains the compactness of our new set of isolines. Lately, we had access to a totally new data sets where we had 80 extra bullets in lead for 22 long rifle. The beauty of that data set is that there's some bullets shot by revolver, by pistol, and by firearms. So at the end, we had 3 groups of different Lee width. My first group corresponds to 6 sister pairs where we typically have a Lee width of 200 pixels. When we correlated them together and do the score adjustment, the non-matching score actually fell right in the middle of my blue reference circle. Taking the second group, 12 sister pairs that actually have 320 pixels for Lee width, when we collate them together and do the score adjustment, well, the non-matching score actually falls right in the middle again in my blue reference circle. And finally, for my third group, where we typically have 420 pixels for Lee width, we collate them together, do the score adjustment, and the non-matching score falls right in the middle here again of my blue circle. And just for fun, we tried the training set of my MB brandage test, where we have 20 bullets. We had typically 670 pixels for lead width. We collate them together and do the score adjustment. And here again, it falls right in the middle of my reference blue circle. So even if we have two different material, 4 different set of lead width, well, doing the score adjustment bring the non-matching score right exactly at the same location in the middle of that blue circle. So now we can actually summarize all that webinar in that slide. If you understand that, you understand everything. So I have a suspected matching pair of bullet. It corresponds to an FAM combination. I mean, it has been shot by a Remington gun. It used cont'd ammunition. They are in copper, but we just don't care. As long as we can grab the 3D information, acquiring them on Quantum, we have the digitized lead profiles right here. And from those profiles, we get the objective identification score, and we get those CNR values, personalized CNR values. We pass it to the score adjustment process that actually removes the FAM dependency and provide the score on the unique generalized RBL graph. That graphic will provide a unique and static separation line that discriminate potential matching pair of bullet. It will also provide a unique and static false match rate set of isoline that will give a probability value, and that probability value will make the bridge between your forensic lab and the court of justice. And finally, a really simple explanation of what is behind the score adjustment process. Respect to a reference FAM combination dataset, for example, our 9mm dataset, smaller lead width, lower slope, and higher numbers of leads produce higher correlation score by totally pure chance. Well, our score adjustment process adjusts or penalizes the score to remove that portion related to chance. This is the only thing that score adjustment is doing. So as a conclusion, marks created on bullets are sensitive to FAM combination, I mean firearm calibers and brand, ammunition type, and material combinations. To apply statistical method, we would need bullets for every FAM combination, generating a huge amount of RBL graph. We don't want this. Yeah. So this is why we put that hypothesis that we validated afterwards. Caliber behavior is instead generated by a small number of class characteristics and roughness variable directly measured from the 3D data, directly measured from the individual lead digitized profiles. So dependency through CNR variables exclude the FAM variables out of the problem. It's not, like I said, it's not exactly that. The class characteristics and roughness variables embed the FAM information. And finally, modeling and controlling CNR dependencies allows us to first manage only one generalized RBL graph, allows us to have a unique and static separation line in a constant false match rate curve, and finally, allows us to reach category 1 for interpretability of correlation scores. The generalized RBL graph is already integrated into the Quantum application. Thank you for your attention.
Thank you, Danny. This is a lot of information and concepts to absorb in a short webinar. I find this research work very groundbreaking, and I hope the attendees, although this was very technical, could grasp the revolution that this brings. I look forward to seeing this being used for casework, like using the 3D microscope. And I invite you to send us questions that you can think about on the email addresses that Danny has listed on the last slide here. I'm sure some of those questions are quite complex, like the subject matter, so we'll take time to answer them. As we've done at the end of May for the other webinar, we've posted a Q&A page on our website for the product page, just where the recording is for the May 28th, and we'll do the same thing here with the questions that we received. I have one question here from Mara Carney. Danny, it's about the synthetic sister pairs. How do you create synthetic sister pairs, and how similar are the sister pairs when they are created synthetically? Well, I know you underlined that the synthetic model is a complex topic on its own, and probably
that's what I said, because it's by itself, it's a topic, and if people are interested, I may actually do another webinar on that. But I didn't address that thing because it's something that is totally apart. Okay, we have a distribution of pattern matching score and line counting score, and I'm actually using that statistics to actually create from an arbitrary profile. I recreate another profile based on the statistics of pattern and line counting score for that specific similarity between sisters for that particular data set. So it's a totally different way to do that. And I would say it's kind of complicated. And we're actually writing a paper right now, and I think we will include that kind of detail in the paper. But I don't think it was really relevant for that presentation here, because it is actually a little bit complicated to explain in a webinar of 50 minutes. So
by relevant, you mean it's too complex and would have derailed
yeah, that's
subject.
it. Yeah, okay. Because the major point here is just to tell people that how do we adjust the score to make it sure that if you put that on the same RBL graph, you actually respect the false match rate value you had at the beginning. That's the major point of that webinar right here. How to create those synthetic profiles, it's another topic. But like I told you, the only thing I can say right here to be, I would say, simple is that when I create a series of 65 sister pairs, I create first 65 totally independent profile. And for each of those 65, I create another profile that respects the statistics of the pattern matching and line counting score between sisters. That's the only thing I can say right here. But digitally, there's a lot of detail, but in concept, that's what I'm doing.
Okay, understood. I have a long question here from Alan at the NIST, Alan Zhang. I'm going to try to read it. I'm not sure we can address that in a couple of minutes we have left, but we can definitely answer Alan. In practice, the caliber and surface materials are matched to the best of their ability to the evidence. Why adjust the FMR curves for a completely different population rather than create an FMR curve for each relevant population?
There's one good reason for that, because when you do your score adjustment, you increase your population on the unique generalized RBL graph. Instead of having 1,000 graph with 1,000 independent data set, you will use your 1,000 data sets all together to have really relevant statistics. That's a major point, actually.
Okay, guys, I think one of his suggestions was to generalize for larger subpopulations rather than one single graph for that's generalized. But I'm assuming this is something that could be worked on and validated as like a secondary work based on what you've just produced. And then validated.
If we realize there are some clusters of behavior, we may actually split that on 2 or 3 major generalized RBL graph. We don't know yet. But for the series of data set I have right now, which include series of material, coppers and lead, and we have different ammunition type. In the context of my webinar, it works amazingly well. Okay, so I don't know. I will keep doing acquisition, and if we have things slightly different, we may actually switch the strategy. But I think the core of that principle works pretty well.
Yeah, indeed, and this is the start of new work. So yes, Alan, it's a relevant question, and I think as with everything that is produced for microscopy, everything needs to be validated by us, the manufacturer, but also by the community and the standards organizations. So definitely, we look forward to that kind of work and refining this. This is a start of a new thing. We believe we're very excited with what Danny managed to do and the possible implications of that. So we need to dig deeper. Sorry, another question just popped in from Eric Warren. What is the significance of the orange warning line that you've added in the latest version of the RBL graph? I think that's the subclass warning coefficient, correct?
Yeah, that's okay. Yeah, that was
that's from another topic.
Yeah, that's another topic. I can answer quickly. It's just that we realized, I think it was 2 years ago at the FT meeting, I presented something on subclass characteristics and all that, but we realized that on the RBL graph between the separation line and the warning line, if your correlation score is between those 2 lines, there's 2 possibilities. You may have a pretty good score based on individual marks, but it may be based on subclass marks. If you are below that, it's a non-match anyway. And if you are above the orange line, it's a match anyway. You have enough individual marks that gives you a match. So this is why you have the ambiguity area between the separation line and the orange line. It just gives you a warning coefficient that tells you, I noticed a significant amount of big lines, and the density of big grooves is high enough to tell me that you may deal with subclass lines. So it's just a warning between those two lines that tells you that you may be aware that you may actually go back and look at the barrel of what of your investigation.
Basically, you just give a warning. There's a coefficient warning that say, hey, you should pay attention. There could be subclasses in that. Okay. So I think that was the last question that that we received on chat. Like again, I invite you to write to Danny or to us, and we will answer you and even post answers if they're for general population, like we did before. Again, Danny and I, we thank you for coming today. We like speaking to this community and showing you what we're working on, and hopefully it helps you do your work. So Danny, any last words?
It's a really interesting field, seriously, and hopefully people will use Quantum because I think it's going to make a difference.
Yes, thank you. And this was a lot of work for Danny to prepare, so thank you, Danny. I really appreciate the time that you spend on this, and I want to wish everyone a good day. Stay safe and stay healthy. So we'll talk to you at the next webinar.
Thanks. Bye.